Let's consider an interesting function. We might have seen these before. These are called surge curves. This one looks something like this. Starts at the origin there. You might notice that it never goes above some level. Can't remember exactly what. It doesn't really matter. We usually just apply some vertical scaling to them anyway. Can I say that this is a horizontal asymptote because the curve never goes beyond that level? That's kind of the impression we might have got from our first video where we talked about one curve that was bounded by a particular y value, and that was a horizontal asymptote because the curve kept getting closer and closer. And then two other functions, square root and log, that were unbounded. Any horizontal asymptote you tried to draw, it would just eventually exceed. But here, we're trying to draw the distinction between something being bounded and something being a horizontal asymptote. What do you say? Remember that the definition of horizontal asymptote is that you can guarantee being within a particular smaller and smaller tolerance as you go farther and farther out in time, as long as you're going to positive infinity, which is not true here for this y value. So it's not true since the curve isn't getting infinitesimally close to that y value. Does this function have a horizontal asymptote? Well, as t goes to infinity, t squared is getting big, but e to the negative t is getting very, very close to 0, much faster than the t squared is getting big. We can't actually prove that here in chapter 1. That's more of a chapter 6 L'Hopital's rule thing, so we're not going to stress about it for now. But we can say y equals 0. I'm kind of giving away the answer here that we would see in chapter 6. So y equals 0 is a horizontal asymptote to the right. So we would say the limit as t goes to infinity, well, I guess I'm mixing up my t's and x's here, is 0. So that's a formula called L'Hopital's rule, or a method. But for now, we can know that that does get closer and closer to 0, but never quite gets there, even though in calculus it could get there and go under and back over, as long as it's getting into a narrower and narrower tolerance band each time. So just because a y value is a bound on something doesn't mean that it's a horizontal asymptote for that thing. The other big question we have to deal with, what's the limit as t goes to infinity sine of t? Take a sec to think about it. Doesn't hurt to draw a picture. Here's sine. What are some candidates? If it did have a horizontal asymptote, what would the horizontal asymptote be? Some people say, well, it's approaching 1 infinitely often. Right? Here's y equals 1. But the same thing we set up here still applies. Yeah, it gets close, but then it gets far away again, and it gets just as far away every single time. So the same thing happens with -1, right? It's getting close to y equals -1, but then it gets just as far away every single time. Some people say, well, it's 0. That limit is 0, right? Because on average we're at 0. It's true that on average we're at 0, but we keep moving farther away and just as far away every time. So we can't guarantee a tiny tolerance around y equals 0 by saying, well, if you just wait long enough, then we'll stay within this tiny tolerance. So we can't guarantee any tiny tolerance around y equals 0. By specifying a cutoff in x or in t. So this limit does not exist. And which kind of does not exist is it? What's happening with the y values? Are they shooting to infinity? Is there a left-right mismatch? Well, we're only going to the right. There's no left. You can't come in from the left from above infinity. So this is the oscillating without settling down kind of DNE. So the limit as t goes to infinity of sine t does not exist. And which kind? It's the oscillating without settling down kind. All right, so that's something important to remember. It works for cosine too, of course. The limit as t goes to infinity of sine t or cosine t does not exist because of oscillating without settling down. That's really the important part of oscillating without settling down. Back when we first learned about it, we were using like sine of 1 over x as x goes to 0. That was just to keep x finite, so we didn't have to deal with t going to infinity. But this is where it's really going to be more important.